Hello, everyone. Thank you so much. Wait, can I advance the slides?
It's the button that's kind of worn off. It's the board.
Okay, got it. So I'm going to talk about understanding the composition of lunar South Pole and also North Pole, because I've included that as well, using thermal infrared spectral data set. Some of the previous talks have set me up a little bit, which is nice, but I'll restart again. So you guys have been hearing.
Did you hold the mic system?
Oh.
Yeah, it's helpful for online.
Okay. So you guys have been hearing the name Christensen feature for really long. One way to understand the composition of lunar surface and thermal infrared is through this feature. It's a specific wavelength at which the real refractive index of a material passes unity. It's an indicator of silica polymerization. What does that mean? That means that it's inversely correlated to, it's a proxy for inverse correlation to silica content. For instance, this is a image of the moon, CF image of the moon. And as you can see, near side mare, which is primarily made up of silica poor minerals, is how I would put it, have CF at longer wavelengths compared to the far side, which is more anorthositic with CF at lower wavelengths. So how is this CF estimated? Currently, in remote sensing, we use data from Diviner, which is an instrument onboard LRO. We use 3 of its compositional channels located around 8 micron to estimate CF. So we have 3 data points, and we carry out a parabolic fit, estimate the maxima of that parabola, and the wavelength corresponding to that maxima is assumed to be the CF. And there has been like an ad hoc cutoffs put up at 6.9 and 9.6 microns. Okay, so before I get into the mapping, there are a few things that I would like to address. One of them is emission. What are the different factors that affect emission? There are several, 2 important ones for the polar regions due to the weird illumination conditions are surface roughness and observer's geometry, more or less. So as we can see here, depending on the location of satellite with respect to the sun, we could see either sunlit slopes at sub-pixel scales in Diviner, by Diviner, or we could see shadowed slopes within a sub-pixel scale. Now, how does that affect emission? So what we observe from Diviner is radiance, and then we convert radiance to emission using a Planck function. Often we currently use a single temperature to go from radiance to emission, but in reality, within a pixel, there are different temperatures present. And the radiance that we observe is a combination of different temperatures instead of one temperature. So in order to correct for that, currently correction has been developed by Alicia Jyoti at UCLA. And I've been using that right now, using a bowl crater model. And I've been using that to calculate CF corrections for viewing geometry. So this is the method. First, we extract the north and south polar summer data, emphasis on summer, and then channel 3, 4, 5, 6, 7, and 8 bend at quarter of an hour. So 24-hour data bend at quarter of an hour. Threshold to remove the values below the noise floor of Diviner. And then we model the native temperatures using the model I just talked about, the semi-analytical bowl crater model, to get rid of shadow effects and like viewing geometry effects. And then some more data analysis is how I put it. You concatenate 24-hour data, estimate mean and median, then CF from the mean and median of each like emission channels. I have put a constraint of 4 hours and 2 hours for North and South Pole, and that is because we could get some noisy values despite putting the previous thresholds. But if a pixel has been like lit for, let's say, 4 hours, it's probably more realistic. It's like a true pixel is how I put it. And then we carry out like projection and gridding. Just to quickly go through what did I mean by summer. So moon has a very small tilt due to which we experience polar summer and also like some south polar summer and north polar summer. And I'm using the subsolar latitude as a proxy for pulling out only the summer data up to 2019. The current spatial resolution of the maps is 1 kilometer. So these are the current maps that I've made. These go from 90 degrees to 80 degrees. This is the mean and the median map, and the current values we are seeing is between roughly, most of them are between 7.8 to 8.1 micron is how I would put it, which corresponds primarily to anorthosites. And there are also like some noisy values beyond that, just by putting all the thresholds. These are the pole brightness temperature maps. And the plan is to use the brightness temperature maps in future by deriving like emission from them to see if we can say more about the spectral, more about the composition using a 6-band spectra instead of a 3-band spectra. This process is still in rectification, is how I put it. This is channel 6 and 7, both mean and median, and this is the distribution of the brightness temperatures across 3 channels, across 6 channels. This is the North Pole CF map. It also displays anorthositic values, as we can see in the corner. Median map is a little more noisy than the mean. And these are the brightness temperature map for the North Pole, again. And the distribution of temperatures looks something like this across the 7 channels, 3 to 7 channels. Then I looked at the variation, latitudinal variation from, I've gone up to 75, not 80. Latitudinal variation of Christensen feature, and we don't see a lot of variation right now, indicating there is not like any exceptional difference in composition that we're observing from current maps, both in median and mean values. Also goes the same for brightness temperatures. In summary, both the poles from our study currently are coming out to be primarily anorthositic in nature. They lack compositional diversity. There are like, okay, the bowl crater model for correcting for emission needs some more improvement in terms for like higher incidence angles that we currently observe on poles. Once those geometric corrections are more robust, this entire process will be revised with the new corrections plugged in, and we hope to have more noise-free, clearer maps. And also like a machine learning method developed by me during grad school to be deployed to get like even more upgraded CF maps. But this is what the summary of the talk is.
Any questions? You're online?
No.
In the
Can
room?
you say a little bit more about some of the machine learning modeling you want to apply to this, like how you might?
So as part of my PhD thesis, okay, I will go back for this because I can do this here. Okay, so if we look at that panel, the last panel, you can see the black and the black spectra specifically is case of an extreme composition in the sense that it's an extremely silicic composition. And in that case, the spectra looks relatively flat. If you do a parabolic fitting on top of that spectra, your values are going to be bonkers. They're going to be like way, way low, which is not real. And solely because of the location of these channels, all the extreme compositions, either ultra-mafic or ultra-silicic, the values do not come out to be quite correct as you move away from 8 micron. So I wrote a model that uses these 3-band spectra to estimate CF, machine learning model, trained on a set of laboratory data and then deployed to moons. And that's the plan to also deploy like polar data set. So that, yeah.